Now, we used this result just to verify what we were what number we got here, okay? But where did this come from? Where did that formula come from? Well, we can verify it. We can verify the formula itself by doing something similar, can't we? Draw yourself up a new set of axes. If I want to make a cylinder of radius r and of height h, okay, what kind of shape, what kind of function would I rotate, revolve around the x-axis in order to get that cylinder? Okay. Well, the height was, we're looking at it sideways, right? That was the height. Okay. So what would you think are some nice typical sort of lower and upper bounds to give you a height of h? Where would you start with?
0.
Yeah, 0 to h, right? So let's start at 0. Let's go up to some arbitrary height, h. Okay, so that's going to be my domain. Then I want to have a radius r. Right now, my radius here is 2. So therefore, what that corresponds to is what this line is, the equation of it, right? So here it's going to be y equals r, whatever radius it is. Okay? So now, if I'm trying to work out this volume that I get, if I rotate it around. Okay, there you go. Can you see it? Okay. The volume is going to be equal to, let's try it. Let's use this formula. Okay. Pi out the front, because it's a constant. By the way, a lot of people forget the pi because they're focused on the integration, yeah. From 0 to h. Okay. Now what's y squared in this case? It's r squared. Good. And it's just a constant, isn't it? Okay. What's that equal to? When I actually evaluate this, what's my primitive? It's just r squared is a constant, so it just comes out the front from 0 to h. Okay. So therefore, I've got pi r squared h minus 0. There's the formula. Okay. So now, hopefully, this process is starting to gain your trust a little bit, right? Where else can we use it? What other kinds of shapes can we make via solids of revolution?
Sphere.
How about cones? We'll get to spheres. I hope. Okay. I'd like to go to cones first because cones are very, very similar to cylinders, aren't they? Okay. Now, draw yourself up a new set of axes. How are we going to do this? What shape ought I to revolve around the x-axis in order to get a cone?
Gradient not equal to 0.
I want one of these, right?
Oh my god.
Right? So there's my cone. If I want it to grow the way that a cone does, and I'm turning it sideways because I'm thinking, you know, I'm rotating this way, then that there is a constant gradient. Right? It's a constant gradient. And it's going to pass through the origin. Right? So, what should we put here? Well, I've got some kind of linear function here. Right? Now, I want a radius of r and a height of h, right? So I'll go like before from 0 to h. And this here, this should be r. Now before it was really easy to work out what the equation of this was. It's just y being the radius. What's the equation of this?
Y equals r on hx plus 0.
So it passes through the origin, right? So it's going to be in the form y equals mx. What's the gradient? It's rise over run. Yes? So rise over run gives me that. Okay? Right. Let's give it a go then. Volume apparently should be equal to, copy pi out the front, 0 to h, okay? And here's my function. Is that okay? We're too sleepy. No, it's not okay because it's y squared, okay? So remember I said people forget pi. The second thing people forget is to square, okay? So this really is all squared, okay? Good, stay with us. Now, this is going to become r squared, h squared, x squared. The r and the h, they're constants that we just decide, right? I want it to be this wide, this high, okay? So I'm going to pull them out the front. Pi r squared h squared. That leaves me with an x squared inside. Okay? So someone tell me please, what's the integral?
x to the power of 3 divided by 3.
Okay, good. We're sleepy, but we're not that sleepy. All right. Now this is interesting because you're like, uh-oh, I've got an h cubed. I wasn't expecting an h cubed because I know what the volume of a cylinder, a cone is. Yeah. Okay. So we're thinking of this shape, right? There's my cone. Okay. Let's evaluate it. See what we get. So I'm coming all the way up here. This is pi r squared on h squared. H cubed on 3 minus naught. Yeah? Okay, so h's are going to cancel. How many are going to cancel? All of these and one of him. Right? Therefore, there's that third which you're so familiar with. Okay? Yeah? Okay, there's one more shape we ought to do. What should we do?
Y equals log x.
That one's the shape that is like a two-sided triangle.
I reckon we should do this guy. Okay? I don't know. Maybe they ran out of plastic or something. I don't know why it's so small. But now, if we want a sphere, right? What shape should I roll?
A circle. A semicircle.
Or a semicircle. Now, interestingly enough, which one should we do? I'll let you have a think about that for a second. I'm going to draw up. I'm going to draw up this shape.
A semicircle.
So far, all we've been rotating is this one at the top, yeah, and that's worked for us fine. Okay, so let's just consider the top half. Okay, r minus r. What is the equation of such a line?
Square root.
Yeah. Okay. So in this case, my radius is r, right? So I'm going to get r squared minus x squared. Is that okay? All right, now what's the volume when I rotate this thing around? Get the shape, okay? It's going to be pi at the front. Now, where am I integrating from?
Minus
Yeah, good. I'm going all the way from over there.
Can you just go from 0 to
I
r?
will in a second, but I'm doing the whole volume. Right? Okay, now what do I put next? What's next in the formula? It's y squared, isn't it? So as it happens, it doesn't matter whether you take a circle or a semicircle, because you'll get the circle back anyway. Right? So this is r squared minus x squared dx. Okay. Now, as you will have noticed, this guy is it's not just any function, it's an even function. Right? So I might as well halve my work by doubling the integral. Right? 0 to r squared minus x squared as y is even. Okay. Everyone okay so far? Yes? Cool. Let's keep going. 2 pi. What's my integral?
R squared x
Yep.
minus x to the power of 3 on 3.
Great. Okay, from 0 to r. Okay. Now at this point it's like, is it really going to come out? Evaluate it and see what happens. Have we formed that integral correctly? Okay, what happens? You stick your r in and you're going to get r cubed minus r cubed on 3 minus what is equal to it, 0? Okay. So what's that equal to? 1 lot of that minus a third of it is 2/3. 2/3 is left, right? 2 pi, 2 r squared on 3, and, sorry, did I write r cubed, sorry, r cubed? I knew something was wrong. Well, that's a relief, isn't it? Okay. So this idea, right, that I can take a function, right, and instead of working out an area, I can work out a volume by going pi r squared, right? It's really, really powerful. Now, there's lots of different kinds of volumes. We've been looking at simple ones and ones where you already knew the results, okay? But we're going to leave that for tomorrow in our double, okay? There's basically 4 different kinds of volumes that we're going to look at. So we haven't even looked at the y-axis yet, but you guys have worked pretty hard, so I'm going to stop there.